Hello and welcome. In this video, we're going to talk about infinite limits and limits at infinity. So our three objectives in this video are that we can evaluate limits as they approach infinity or state that they do not exist, and that we can use those limits to find horizontal asymptotes. And lastly, that we can analyze the behavior of limits as they approach vertical asymptotes. So let's go ahead and jump right in. So in previous lessons, we have taken the limit as we approach a particular value, sometimes one-sided, sometimes two-sided. In this section, we're going to talk about taking the limit as we approach infinity. So what's happening to a function as we go forever to the left or forever to the right, approaching negative infinity or positive infinity. And that's called a limit at infinity. And really what we're talking about here is what's happening to our function at the end behavior. If that limit is something finite, then we say that that limit exists. So in this case, the limit exists because L is a finite number. It's also possible that as we go towards infinity, our function is forever getting bigger or forever getting smaller. That would mean that our limit is positive infinity if it's going up forever, or negative infinity if it's going down forever. But regardless, that would mean that that limit does not exist. So let's think about what causes those limits not to exist. One of the things that causes a limit to go towards infinity or towards negative infinity is having a vertical asymptote. So we might have a value that's going forever upwards towards infinity. A vertical asymptote occurs when the denominator is 0 and that factor does not divide out, because we learned previously that if the factor divides out, then we actually have a hole in the graph. So vertical asymptotes are x equals values that cause the denominator to be 0. So for example here, if we had this function, x equals 2 would make the denominator 0, so there's a vertical asymptote happening at x equals 2. And we're going to talk about what happens if we take the limit as we approach 2 later on in this video. But just a reminder, vertical asymptotes, which we can abbreviate VA, occur when we make the denominator of our fraction equal 0. Horizontal asymptotes, on the other hand, are y equals asymptotes. And the way that we can find them is by taking the limit as x approaches infinity of our function and taking the limit as x approaches negative infinity of our function. Again, if those values are finite, then those values, y equals those values, are our horizontal asymptotes. So let's look a little more at horizontal asymptotes and how we take limits at infinity. So for right now, we're going to focus on rational functions similar to the one down here. So a polynomial over a polynomial, that's what gives us a rational function. And we're going to start with the fact that if we take the limit of some constant over a polynomial, that limit is going to be equal to 0, because basically what's happening is the bottom is growing and the top is not changing at all, which means that this is going towards 0. But let's generalize this a little more for polynomials or for rational functions. If we think about the highest degree term in the numerator and the denominator, and which of those terms is growing faster, that will allow us to make a determination about what's happening as we approach infinity. So for example, if we're taking the limit as we approach infinity of x to the third over x squared, and let's just add a constant here. If we were taking this limit where the degree of the numerator, in this case 3, is greater than the degree of the denominator, in this case 2, then our limit is either going to be infinity or negative infinity, which means that this limit is not going to exist. And we'll talk more about that in just a minute. If the reverse of that is true, if the degree of the denominator is greater than the degree of the numerator, then the top is growing slower than the bottom. So you could really think about this in terms of limits as as some constant over x plus 1, right? Because it's almost like we could divide two of these x's out when we're thinking about the behavior of the limit. And this, we just said this limit is going to be equal to 0. So if the degree of the numerator is less than the degree of the denominator, we can say that that limit is going towards 0. If the degrees are exactly the same, then we're going to just divide the leading coefficients. And that's when we're going to have horizontal asymptotes. So for example, the limit as x approaches infinity of 2x squared over 5x squared plus 1. The degree is the same, so we can think about this as the x squareds as we go to infinity are dividing out, and all that's left that is changing is the 2/5. Now I'm going to show you why this thought process works by working through this limit in this for instance problem. You don't have to show this particular work, but I want you to understand where this idea comes from. So the term in the numerator and the denominator that has the largest effect on the fraction as we go towards infinity or negative infinity is the term with the highest degree. So what I'm actually going to do is I'm going to go ahead and factor that term out. So here I have factored in purple x to the 5th and 3x to the 5th out in front. If I distributed this back out in the numerator and the denominator, I would get here. So what I want you to see is as we go to infinity, the 1 isn't changing. 2 over x to the 3rd, that limit is going to 0 because the denominator is growing and the numerator is not. 1 over x to the 4th, that limit is going to 0. 1 over 3x squared, that limit is going to 0. 1 over 3x to the 5th, that limit is going to 0. So this limit is going to be equal to the limit as x approaches infinity of x to the 5th over 3x to the 5th, because if I just multiply by the 1 here, that's what I'm going to get. Now, according to properties of limits, we can simplify our x to the 5ths, and all that's going to be left here is the 3 in the denominator. So this limit is going to be equal to 1/3. So that's the rationale behind what we're doing. You don't have to show that factoring out step. You just need to look at the behavior of the terms with the highest degree. So let's look at a couple examples. All right, here we go. On number 1, we only care about the degrees with the highest term. So I have 3x squared and I have x cubed, which means that the top is smaller than the bottom. So we would say that this is slow over fast, because a squared function is growing slower than a cubic function. So that means this limit is going to be equal to 0. Again, this is because we're approaching infinity. That also means that there is a horizontal asymptote at y equals 0. On number 2, I have 11x to the 5th and I have x to the 4th, and we're approaching negative infinity. So as we go towards infinity, those are the only two terms that really matter, 11x to the 5th over x to the 4th. If I simplify here, I'm getting the limit as x approaches negative infinity of 11x, right? Because 4 of these can divide out. Well, this is going to be what? 11 times negative infinity. This is approaching negative infinity, or it does not exist. It does not exist and negative infinity mean the same thing. I want you to go ahead and pause the video and try numbers 3 and 4 on your own, and then unpause the video and see how you did. Remember, the only term that matters if we're taking a limit as we approach positive or negative infinity is the leading term. So hopefully you had time to work through this. On number 3, we're just going to divide those leading coefficients, and that's going to give us 14 over 3. On number 4, I want you to think about what would happen if you expanded out the numerator. The denominator's leading term is obviously 5x cubed. If we expanded this out, but I'm not actually going to do that, this would become x squared, and then I would multiply that by 2. So the leading term is going to be 2x cubed. So now the degree is the same. So this limit is going to be equal to 2 over 5. So number 2 has no horizontal asymptotes. Number 3 has a horizontal asymptote at y equals 14 over 3. And number 4 has a horizontal asymptote at y equals 2 over 5. So now we can see how limits tie to horizontal asymptotes. If you were asked simply to find the horizontal asymptote or all horizontal asymptotes, you would need to make sure that you look at both the limit as we approach positive and negative infinity to identify if there is more than one. All right, let's talk about one last thing. Let's talk about what happens if we take the limit at a vertical asymptote. All right, here we go. No matter what, if you take a limit and the function approaches infinity, that limit does not exist. But if it happens to be that both sides of the function, the left and the right, are going towards the same infinity, then we can be specific about how it doesn't exist. So we could describe the infinite limit as positive or negative infinity. So if you look at these two graphs on the left over here, both on the left and the right-hand side, they are approaching the same infinity, which means, yes, we can say that those limits do not exist, but we are specifically being asked, how don't they exist? This one doesn't exist because it's approaching positive infinity. This one doesn't exist because it's approaching negative infinity. The two graphs on the right aren't doing the same thing on both sides, which means no matter what, if we're being asked about the two-sided limit, all we can say is that two-sided limit does not exist. Now, let's look at this from a function perspective. If we're looking at the limit as x approaches 3 of 1 over x minus 3, we can't use direct substitution because we would get 1 over 0, and that doesn't exist. That means we now want to look at one-sided limits. So what I want you to think about is if we approached 3 from the left of this graph, would we get something positive or something negative? So if I was a little smaller than 3, then in the denominator I subtract 3, this is going to give me a negative number. So the left-hand side is going towards negative infinity. If we approach 3 from the right, we're going to get something positive, right? Something bigger than 3 minus 3 is going to be something positive. What that means is this overall limit as we approach 3 just doesn't exist. It's like one of these graphs up here where it's not approaching the same infinity from both sides. If we look at number 2 and we substitute in, we can't use direct substitution, so we need to look at one-sided limits. So if we look at the limit as x approaches negative 2 from the left, of 3 over x plus 2 squared. That's going to be a positive number because no matter what happens with negative 2, I'm going to square that. That's going to be a positive number, which means the exact same thing is going to happen from the right because we have x plus 2 quantities squared. So that's also going to be infinity. That means we're allowed to say that this limit is actually equal to infinity, which tells us how it is behaving. All right, I want you to go ahead and pause the video and work through number 3 on your own. I'm going to start by actually simplifying this function. I know that this factors to be x plus 3 and x minus 3, so I can simplify this function. So this limit is going to equal the limit as x approaches negative 1 of 1 over x plus 3 times x plus 1. Let's look at that limit from the left. If I have something slightly smaller than negative 1, this is going to be a positive number, but this will be a negative number. So this is going towards negative infinity. If I approach negative 1 from the right-hand side, x plus 3, that's still going to be positive. And if I'm slightly closer to 0, then this is also going to be positive. So this will be positive infinity. That means this original limit does not exist because the infinities on both sides don't agree. All right, let's go ahead and wrap up this video. Our goals in this section were that we could define or evaluate limits that approach infinity or state that they don't exist, and then to tie that to horizontal asymptotes. And lastly, that we could analyze the behavior of limits as they approach vertical asymptotes. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.